In the next part, we will talk about the observations or model results of the different terms in the TKE budgets. So this is what we call the TKE budget equation. We have done some part of it. So we have the first term here, which is the change of the average TKE over time. This is the local change, and we call this the storage of TKE. And then here is the first term on the right is the buoyant production or loss. It's due to the heat flux in here, right? So we call this the buoyant production because it's mainly due to the convection. Okay, and then this term is what we call the mechanical shear production. You can see that this term is actually the shear itself, the change of the mean state wind over height. So this is how shear forms if we have something here. If we have a shear in the vertical dimension, we will have some production of the TKE. And we also need, we also need the vertical transport of horizontal momentum. This is the covariance terms. Okay, here is the affection of the TKE itself. E is the TKE, right? So the affection of the TKE itself by the turbulent vertical motion, and also the gradient of this, the change over height, the change of this term over height. Okay, and we have already mentioned this. We will ignore this term because P prime is very small, W prime is also very small, and it's also very hard to measure, so we choose to ignore this term. And I think I have gone over the dissipation term. So in here, TKE is not a conserved variable. It's not conserved, even though it's called energy, but it's not conserved. It's dissipative. It has to be dissipated at this end of the spectrum. And the dissipation term exists when the TKE is not zero. So whenever there is TKE production, there should be dissipation. So energy is flowing this way. And turbulence tend to decrease or disappear over time because of the continuous dissipation over this end. And unless it can be generated locally or transported in, we will have destruction of TKE eventually. Okay, and then here the third term and the fourth term, this term and this term, they are the most important among the terms on the right because they are representing different processes generating turbulence. So this one is the buoyant production or loss. So it's the production of the TKE due to heat flux. So it's the buoyant production. And this is the mechanical turbulence. So it's due to the shear. So two processes here. This is just another graph showing you the energy cascade. Some people like to use this graph to represent this idea, the cascade of energy. So it's the injection of energy in the production subrange, and then the energy transfer from the larger scales to the smaller scales. And here the energy is dissipated. Okay, so we cannot talk about boundary layer meteorology without talking about the observations. It's very important to talk about observations. So here is the time and space variations of the TKE. So by time is x-axis here, and by space is the y-axis here, which is the height. So if we do the average of the TKE, and then we find out the change of the TKE over time. So here are the values of the TKE. We know that in the morning time, the increase is small, okay? And then in the after the noon, during the afternoon, the production of TKE is much larger. The largest is being around 0.4 or 0.3 kilometers. Okay, and then you can see the vertical profile all the way to a very high level. You can see that there is the whole portion of the PBL having TKE increase afternoon, and then after that it decreases. Okay, and then this the dramatic increase in the early afternoon, and during the process the non-turbulent free atmosphere is entrained into the mixed layer. So it is talking about this, the entrainment zone. Okay, and we call this spinning up. So the PBL is spinning up and getting the air in the free atmosphere to involve. And then after that, after the sunset, we have dissipation larger than the production of TKE, and we have the spinning down. So there is a diurnal cycle. You can see that the first day we have production of TKE, and the second day we also have the production of TKE. Okay. This is also another observation. This is the X. I believe the X-axis is time, and then Y-axis is the TKE. It's not the change over TKE, it's just the TKE. So we can see that it increases over time, and you can see this. There is a range here, which is the range of uncertainty of your measurement. And oh, sorry, this is not the observation. This is the model. It's coming from the computer. Okay, so if we compare the simulation with the observation, we can see the increase of the TKE over time comparing to the increase we see in here. Okay, that's because we always have less data than we need. We only have measurements for a certain level, but for the model we can have data from different layers. And here is also model results of the storage of TKE, which is this term. Oh, not this term, sorry. Also TKE in this dimension. And then here is the height. So this is a model result. So we can turn on or turn off anything in the model. In here we have turned on the buoyancy, which means that we have solar radiation heating up the surface, and we have all the thermals, and then we also have the shear. You can see that the shaded area is where we have both of these processes on. You can see that it's larger near the surface because of the shear, and then it's rather mixed. This is the mixing layer. The properties are mixed. And if we turn off the shear, what happened? We only have the buoyancy. Active in the model. What would happen? The TKE is strongest at around 0.3 kilometers height, PBL height, which means that maybe the heat flux, or maybe some processes are contributing very much in this level. And you can see that the TKE increases in time, which means that this term is positive. Okay, now we can explain the buoyant production term. So you can see that this is actually the heat flux that we have talked about. So this heat flux profile is very similar to this one in here. And the terms of the TKE budget, so here is 0, and then this is the normalized TKE values. It's normalized against the value of this term 3, the third term at the surface. So you can see that the vertical flux of the heat, or theta prime, decreases linearly with height, which is similar to this one. We have already explained this one. And the surface term is used to normalize all other terms, so you can compare the strength. For example, if we compare the strength of this third term with the fourth term, the shear generation, you can see that for some of the turbulence, or for some of the eddies, the shear generation is contributing more to the TKE production. And also there is a part where it's contributing less. So there's a range of values for this fourth term. Okay, next. So here is also the buoyant production around sunset. You can see that the third term here, so this is height, and then this is the change of the TKE over time. So you can see that the third term is actually destroying the TKE because it's on the negative side. At the nighttime, we have radiative cooling, the long wave radiation from the surface of the Earth, and then we have the statically stable condition. So the heat flux probably is negative, and then we know that we have destruction of turbulence because of the stability, or because of this stable environment. So the parcels tend to move back to the original position, which means that turbulence cannot form. Okay, and the negative values here mean that it's TKE destruction. It's destroying the TKE, or it's contributing to the decrease of the TKE. Okay, so next we talk about mechanical production or shear production. So in here you can see the wind profile. It's pretty much very similar in the mixed layer, except that for the surface layer it's decreasing with height, which means that if we take a look at this term, it's decreasing with height, so this is negative. So when this is negative, when this one is negative, this one is positive. The momentum flux is positive because of the, okay, sorry, in here, in this case, this shear is positive because when you're going up, the wind is stronger. This is smaller and this is larger. So this is positive, which means that the horizontal momentum is being transported downward because this has a higher velocity, which means that it can be, the horizontal momentum U prime can be transported downward. This is a weaker wind area. If you remember the random movement of the molecules, we have explained that in the last lecture. So which means that this term and then this covariance they should have opposite sign. Whenever we can draw this kind of shear diagram, you know what I mean. Okay, they have opposite signs, and then that's why we have positive shear production. And in the mixed layer above the surface layer, the wind speed varies very little in here because of the strong mixing, and it leads to near zero production. So you can see that it's near zero production in here, but it has a very strong production near the surface. Okay, and at the top there's a little TKE production because of we have geostrophic wind in the free atmosphere and subgeostrophic wind in the PBL, so it's a little bit weaker than the wind above that. So that's why we have a little shear production in here. Okay, so this is a question asking you the signs of the different terms in this shear production. Okay, for A and B, this is A part and then this is B part. Choose the most possible shape for the turbulent eddy. So you know that this term and then this covariance, they should have opposite signs. So you can guess the sign of a certain terms with these diagrams, and then you can choose the appropriate one on the right. Okay, and then also write down the signs of the momentum flux for all the 4 terms. Okay, so here is from observation, I think. So this is showing you the boundary between the dry and the moist air. So below that, it should be the PBL, and then above that, it should be the dry free atmosphere. And also for this one, we are giving you 2 graphs here because this is from the mechanical turbulence. You can see that the graph is messier than this one. This is from the thermals or from the buoyancy generated turbulence. So most of the times we know that both buoyancy and shear production happens. So both of the 2 processes, they happen together. And at nighttime, we only have the mechanical turbulence. So that's why term 4 here, which is this shear production, is very important at night time. And this 4th term it mainly produces horizontal turbulence. I think I have explained this. So it's the main difference between the turbulence happening at nighttime and turbulence happening at daytime. At nighttime, it tends to produce horizontal turbulence because we only have mechanical production at night. And then it's more chaotic because it's horizontal, so it can be moving around. Okay, and term 3, it's the buoyancy term. It produces vertical turbulence, so you can see kind of the thermals. You can actually see the thermals happening in here. So this is clearer because it's just this dimension, but this one is just going back and forth and it's messier. Okay, so the 5th term is the turbulent transport. So it's the transport of the TKE itself by the vertical turbulent wind. Okay, so it's a flux divergence term, the 5th term. So this is the flux. And the divergence mean we have already explained the meaning of divergence. So more flux into the layer, which means that TKE is generated. So if we have a gradient over this flux term, we will have convergence or divergence. When we integrated the whole PBL, we know that this term is 0 because it neither destroys or creates turbulence. It is just moving the TKE around. So it's just moving TKE from one place to another place, and if we add the term up for all the layers, it will be 0. And here I'm showing you so here is the observation, I think, and then this is the range of the measurements, or the range of the uncertainty. Okay, and the x-axis is the change of TKE over time due to this term, and then this one is the normalized height. You can see that in here we have the divergence of TKE flux. This arrow is smaller and it's getting larger, which means that it's a divergence. And here, this value is larger than the values here and the values here, which means that it's a convergence of TKE flux, which means that TKE increases with time, so it has something to do with the sign of this term. So this graph means that some TKE is produced near ground, and the TKE is being transported up to the top half of the mixed layer. Okay, so next is I think there's something wrong with this graph. Okay, so here we have the axis for the dissipation, also for the dissipation, and then the height, and then the height here. And you can see that because we have a square here, we know that the dissipation is always negative. It's always destroying the TKE. And it's larger for smaller eddies. Why? Because if you put a smaller number here, then the TKE will be larger. So smaller eddies, small length scale, and it is greatest at the bottom. You can see it in here and in here, because the eddies here are the smallest. Okay, and over daytime you can see that the dissipation is relatively constant over height due to the very strong mixing. And then at the nighttime it decreases rapidly, because it also depends on the strength of the TKE. So at the nighttime, most of the turbulence are happening near the surface due to the wind shear. And only shear can generate turbulence at nighttime, because we don't have the buoyancy effect during the nighttime. We don't have the thermals during the nighttime. Okay, here is also showing you the dissipation of the TKE over a day. So we can see that it's increasing over time. It probably is due to the fact that we have increasing strength for the TKE over a day. Okay, so this page is optional. It's telling you that, so on this side we have larger eddies, TKE is produced here, and then on this side we have smaller eddies, TKE is dissipated here, and the line here is showing you the flow rate. So you can see that the large amount of energy flow through in the middle sizes, but no net energy accumulation. So it's the largest flow in the middle sizes, but no energy is accumulated in here. Here is another graph showing you the spectral energy of the larger eddies here and the smaller eddies here. And we have a range in between, which is called the inertial subrange. It's the range where the energy is flowing through from larger sizes to smaller sizes. Okay, I just put this line here to remind you that we have already talked about this the spectral energy or spectral intensity for the larger eddies and the smaller eddies. You can imagine the flow from this sizes to this size. There's very little energy in between, but it doesn't mean that there's no energy flow in between. Okay, this is just reminding you what wave number is, because the sizes here are shown by wave number. This is the wave number, or the wave number in here. Okay,